Okay, let's start. Hello, everyone. Thank you for coming. My name is Pavel. I work at Align Technology, and today I want to talk to you about fun with type erasure, and specifically about implementing a value wrapper for polymorphic types. Today we'll talk about, we'll remember what is polymorphism and pointer semantics connected to polymorphism in C++. What are the most basic possible implementation of value wrapper using std_any, and what are its drawbacks. We'll implement our own minimal implementation of value wrapper, very economical, also with small object optimization. We'll see what else can we do, and in the end, if we have time, we'll see at some other things that we can do to improve maybe our implementation and make it more useful. The idea of a value wrapper comes from Jonathan Bokora from his keynote at Meeting C++ 2020. I recommend it to watch this keynote. He talks about this idea towards closer toward the end of his talk. And let's start with an example. So we have a polymorphic base class. I know that, yeah, it's beaten to death, but please bear with me. And we have, in this example, 3 types that are derived from that polymorphic base. And in general, we can have any number of types that are derived from our polymorphic shape base. And we cannot know beforehand how many and which types are derived from that. And it can be used like this. We make unique pointer to star, and interesting things can be done when we assign it to pointer to shape, to its base class. And I like to think that this point, when the assignment happens, we can see type erasure, because we lose information about the actual type. And what we left is just pointer to base class. So in this application, we have pointer or reference semantics. We cannot generally copy or clone values. So we cannot make a clone of some existing value that we hold by pointer to base class. Oh, sorry. And generally, we have to use memory allocation, because we have to have an object on the heap, so it doesn't destroy when we get out of the scope of the current stack or whatever. So what interesting things can we do with such design? Here we have a collection of shapes, pointers to shapes rather, and we can add an ellipse, we can add a rectangle, and we can add a star. And let's say that the user wants to make a copy of, wants to change the size of the shape with index 1. So he probably selects a shape on his screen and changes the size. And also he wants to make a copy or a clone of that shape, and also wants to change its size to his desire. With unique patterns, we have no trivial or obvious way to do that, but we could do that if we had some kind of value wrapper. And instead of operator arrow to access the pointer, we use value call to access a reference of the underlying value. And here we practically do the same. We change the shape of the rectangle. the shape with index 1. And also we make trivially a clone of that shape and then change its size. We can cheat a little bit here by calling a placeback instead of pushback. This is, I consider it cheating because the guidelines say that we should use pushback for one argument instead of in placeback, because in placeback calls all the constructors, including explicit constructors. And in this case, we have explicit constructor, and we want explicitly to call this explicit constructor. That's why we kind of can use in placeback here. So here is our basic solution using std_any. Let's see what it contains. It contains default constructor that constructs an empty wrapper that doesn't contain any value. Then we have a constructor from arbitrary type, and we have to constrain it to accept types that are derived from interface. And also, we want to constrain it to not participate in copy construction and move construction, because we want these operations to be generated for us by the compiler. And that's why we see these two conditions in the requires clause. We can use enable if in pre-C++20, but with practically the same form. But this is non-trivial and hard to write correctly. And for the rest of the talk, we'll stick to C++20 requires. So here's our constructor that constructs the contained value from any value that we provide to it. Next, we have value access functions, value, and function that tells us if this instance has value. It's called has value. So in the implementation section, we have std_any for data storage, and we have a pointer to function that receives a reference to std_any and gives us back a reference to the interface. With this function, we will retrieve a reference to the underlying object, rather. So here's the constructor. We construct the object in the storage itself by forwarding the value, and the next is initialization of the getter pointer to function. We initialize it with this lambda that receives reference to any, and using anycast, we retrieve a reference to the underlying object from that storage. Notice that we use dkt from t, that is like the actual type that we provided in the constructor. And then we convert that reference to interface. So this is not only retrieval of the underlying type, but also conversion from reference to that type to reference to interface. So there might be some pointer adjustment, so to speak. Next, we have our access functions. In the first non-mutable function, we have const. We'll come back to that a bit later. And the function that tells us if this instance has value just asks this question to the storage itself. So this way, we have all the operations necessary to work with this type. We have initialization, copy, move, copy assign, move assign, And also we can access the underlying value by the reference to the interface, to its base class, and do thus probably something useful with it. What drawbacks do we have with this solution? The retrieval of the of the reference to interface is rather costly for one instance. So here I forgot, of course, to replace operator arrow with the value, but there should be a value getting reference to interface. And in there we have a call to getter. This call by pointer to function that we initialized in our constructor. And inside that function or lambda that we initialized it with, we have another rather expensive relatively operation of anycast that checks the type of the contained value in runtime and also can involve so-called Erasure call to get the actual reference to the underlying type. I think this might be costly, so we'll address that later. Other drawback is that all the implementation that I examined, that is MSVC, libstdc++, and libc++, have different implementation, including the size of the actual std object and the size of the small buffer for small object optimization. For example, for MSVC, we have 64 bytes total. So the object of type std will occupy 64 bytes on the stack or in the heap. And it has this amount of bytes for small object, for small buffer. And this expression is so complex that I needed a scientific calculator to evaluate it. And it evaluates to 48 for non-trivial types and also 56 for trivial types. We'll see how it's done a bit later. So for MSVC implementation, we have in the std object a small buffer plus pointer to function table plus pointer to type info. For libstdc++ and libc++, which are implemented kind of similar, we have 16 bytes for the size of std and 8 bytes for small buffer. For libstdc++ and for libc++, we have 32 and 24 bytes respectively. So this is all for x64 configuration. And note that plus to all this mess, including the pointer to function table, we have to bring with us a pointer to our function table, which is the getter. In this case, it's just a pointer to function. So I thought that this is a good justification to implement our own type with all the bells and whistles. And here's it. Here's the keys to it. So we have our template, in this case, struct template. We parameterize it with the type of our interface. Then we have default constructor. We have constructor for putting arbitrary objects inside our wrapper. We have copy constructor, destructor, assignment operator, and functions to retrieve the reference, and the function that tells us if this wrapper has value. In the private section, we have a constant for small capacity, small buffer capacity, which we choose to define equal to 24, like in the libc++, I guess. And we have a union with small buffer and pointer to big object, depending on which we have at this current moment. And also we have a pointer to table function. Let's start with the private section, the implementation. So we have the our constant that tells us how big the small buffer should be. We define for our convenience a template variable that will tell us if this concrete type is considered to be small. That is, if our small buffer can accommodate it, and if the alignment of our small buffer is compatible with that type. Next, we have a union, which contains a small buffer and a pointer to our big object. And we use either of these names. Let's say that depending on which type of object we currently store. Okay, the next is in the private section is struct methods, which contain three pointer to functions, pointer to function for destroying, copy construct, and getting the reference to the underlying object. And also we have a pointer to an instance of this object, which contains pointer to functions. So we don't bring with every instance these three pointers, and we can just point to some static object which contains pointers to all of these functions. And here we have a static function which provides for us functions for, or rather method function table for small objects, and also a static function that provides us with a function table for big objects. And we have a static template variable, or rather variable template, which depending on the type, stores function table for small or big objects. Okay, let's get back. Oh no, let's examine what how these functions are implemented. And for the function for which returns function tables for small object, depending on the type, we have function for destroy, which is initialized with this lambda, which basically reinterpret casts pointer to small buffer and called the destructor. Then for copy construct, we have placement u using the address of the small buffer, to which we construct, or rather copy construct the value from the source argument, reinterpret casting it to const type. And for get, we just reinterpret cast the address to small buffer and just return it. For big objects, it's kind of similar. We have our function template for big objects, which returns function tables. And for destroy, we just static cast the address to our big object to the actual type and delete it. For copy construct, we static cast the source argument to the actual type and just new, let me show it, just new a new instance and assign our big pointer an address to this new instance. And for get function, we just static cast our pointer to big object to the actual type and return it. Now we go back to the public interface, and we have default constructor defaulted, which constructs an empty wrapper that doesn't contain any value. The next is the constructor that acquires a copy of the object that we give it to it. And here we can see that we use the constraint that the type of the object must be derived from interface. And in the constructor, we initialize the pointer to methods with table to pointer to a table to the static variable for the actual type of the object provided, the dkt or from t type. And within the constructor, if the actual type is small, by our definition, we just we use placement u to construct the internal, the contained value from the argument. And if the type is big, we just new a new instance for the actual type and save the address to that instance into our variable for big objects, pointer to big objects big. Other special members are copy constructor, in which we just copy the pointer to methods from the other instance, and if other instance contained a value, we will copy construct an instance in this object from the value from the other object. And the destructor checks if we have value, and if we do, it calls destroy to free the resources, destroy this instance, and free the resources. And other important special member is assignment operator. Here we use this contraption to support or defend from self-assignment. I'm sure this can be done more elegantly, but for the purposes of this talk, I think this will do. Next, we check if this instance has value. We destroy this instance, this value, and assign nulliter to pointer to methods. This is our invariant, and that this instance has no value. This is needed to guarantee at least a weak exception guarantee. So when, in case the constructor throws, we are not left with the methods pointing to some random inconsistent table. So if the other value has the other object has value, we call copy construct to construct this instance from the other instance and assign pointer to the table if the copy construction went successful, if it did throw an exception. And this is the easy part that's left. We have access functions through which we access to our underlying object. And for mutable non-const, version, we discussed constantness of the reference away because it's safe to do this in this case because we know that our object is not const, it's a mutable object. And the other one doesn't need const cast because we get a const reference from the get object, from the get function. And the other one is has value, which checks if pointer to methods is not null. If it is not, that means that we contain some value. So to illustrate how it works, we have this dummy implementation that does nothing useful and just outputs to console some text. And so we have, if we write the code on the left, we can get the output like on the right, and all the operations work, even though we defined only copy construction and copy assignment without move operations, move special methods. And it shows because when we try to move, it uses copy constructor instead of move constructor. And when we try to move assign, it uses also copy constructor instead of some other means. We will get to that a bit later, how we on time. We're kind of good. So let's do a trade-off. When we get reference to value, we have to call a function by pointer, and this can be expensive. And if we frequently want to get access to the value, it can be expensive. So let's sacrifice a couple of bytes and store a pointer to interface in our implementation, in our object. So we have rather simple implementation for value retrieval functions. We just return reference that we just how do you say it? Never mind. We use a pointer to return references from these functions, and of course we need to put some address to that pointer when we construct or copy or whatever our contained value. And we do this in the constructor, very simple, by adding assignment from the address that we got from placement new in the case of small object, or the address of the instance in the case of big object. And the next change is that we get rid of the get function or function pointer. And we have to a little bit change the implementation of the copy construct functions that live in the tables. In this case, it is very similar to the change in the constructor. And here, this is again very similar to the change in the constructor. We just put an address of the instance that we created just now into the pointer that lives in our object. So let's compare what we got to the any implementations across libraries, standard libraries. In MSVC, we have a kind of pointer to type info, which they pack in lower 2 bits, the flag, which tells which type of object is contained in this instance. We have 3 types, 3 categories of objects. It can be trivial data, in which case we use small buffer for trivial data and just memcpy, CPY, how do you say it? Memcopy. when we need to copy or move or whatever object of that type. Or we have a small buffer plus pointer in the union for non-trivial small objects and big objects. And also we have a pointer to function table, which is populated depending on the type of the object. So for small objects, it is populated with pointer to table for small object, and analogously for bigger objects. Oops. Okay, yeah, we got it. For libstd++, we have kind of similar to our approach, or something slightly different from our approach. They have what I call do all function, pointer to such function. They when they call it, they supply this constant for operation. It can be copy or getting a pointer to the object itself, or getting pointer to type info or whatever. And with this third argument, they supply a pointer to necessary data using this union. So, for example, they can, with some operation, get a pointer to object, or with the other operation, they can get a pointer to type info. And plus to that, they have a union of small buffer plus pointer that they use for small objects or big objects. In libc++, they have very similar design to libstd++. The difference is that in the do all function, they spell out all the necessary arguments, and they supply different arguments depending on the action. And also, plus to that pointer to function, they have pointer to object, to big object, or small buffer in the union. And finally, our implementation that is rather different, I'd say, from the purpose of std, but nevertheless, I think it's useful to compare the implementation to the standard one. So we have small buffer plus pointer in the union. For small objects and big objects, we have pointer to method functions. This is kind of averaged out across all the implementations, something not quite the same as any of them, and kind of average or like mean across all of them. And also plus to that, we have a pointer to interface, which we use to retrieve a reference to the underlying value. Oh yes, I should have, when I was talking, to animate all the points. So here we have pointer to methods, and here we have pointer to interface. And let's get back to the move operations. And I have to say that all the standard implementations implement this kind of optimization or trade-off and use move operations if the initial type allows it. So to be able to use it, we have to add a condition to our isSmall variable, which allows only those types that have no throw of move construction. Because if a type can be accommodated by the small buffer, but does not provide no throw move construction, we can't use that operation in our move construction, because our move construction will not be no accept. For that reason, if the type doesn't provide no acceptance construction, even though it can be accommodated in the small buffer. We consider such a type as big type and store it in the pointer to big types. And also we have to have a pointer to move construct function in our table of methods. And here's what we have to add so we can use it. In the table for small objects, we add move construct function, which is very similar to copy construct, and instead it just moves value from the source argument. And for table for big objects, we just move the pointer from the other argument, from the source argument, and set the source argument empty. That is, we just move the pointer to our instance and leave the source instance empty. That is, all the values will be null, and we'll not be able to get anything from that moved from object. What else should we do? We have to implement the move constructor, which we just do very similar thing to copy constructor, except we call move construct instead of copy construct. And we have to implement move assignment, which is slightly simpler than copy assignment because we don't have to worry about exceptions because all our operations are guaranteed to be no except or else. And here is the defense from self-assignment. If our instance has value, we destroy it and then just copy or rather move the value from the other instance to our instance by calling move constructs. And then we just return this. And this is much better because now when we move value, this is for smaller objects. When we move value, we use move constructor instead of copy constructor. And when we move assign, we use also move constructor instead of copy constructor. And we can make it even better, which we will return to that a bit later. We have time for that. So let's look at the difference of implementations or behavior rather of our implementation and std. For small objects and move construction, both our implementation and MSVC std just move. They don't do anything else. And move construction in libc++ and libc++, they move the value and then destroy the initial value, the moved from value. So this is kind of reasonable. Next, we have move assignment for small objects. Here, our implementation and std do the same thing. They destroy the current value because we have to, and then they move the other value from the moved from instance. We call here destroy because we do not rely on move assignment, and we have to use only destructor, copy constructor, or move constructor. So this is kind of reasonable. Again, libstd++ implementation destroys this object, moves, and then destroys the initial object. This is also kind of reasonable. It leaves the moved from object empty, and libc++ does the funniest thing. So I have no means to show all of it in this slide. So we're gonna have to need a bigger slide. And move assignment is implemented in terms of swap. libc++ gives us this kind of thing that I think can be improved to reduce the number of moves. And yeah, I think here is an opportunity to do some work and to make it better. So what we are left with is copy assignment, and for our implementation, we just do destructor and copy, which is kind of reasonable. For MSVC and libstd++, we copy construct, then destruct this instance, and then move the copied instance into this instance, and then destruct the copy. This is needed because it wants to make a strong exception guarantee, which means that if the first copy throws, then the instance that we want to assign to is left in the same state as it was before the attempt to copy construct. So probably by tradition, libc++ does some different thing, some funny thing. It happens because it is implemented, the copy assignment is implemented in terms of swap. And again, here we can see a bunch of moves that I think can be eliminated, but whatever. So let's get back to the assignment and move assignment. And here we can use opportunistically move assignment and move assignment instead of destructors and copy constructors and move constructors. And let's try this. At this point, what we have to this point, you can be happy with and not add operations for assignment and move assignment, but we will do this just to see what happens. So we have to add another operations for assignment and move assignment in our table. And here for the function table for big objects, we have to add an assignment function that if this type is copy assignable, it just uses copy assignment. And if this type does not support copy assignment, we have to destroy the old value in the destination and copy construct the other value, the value from the other value. So even though the type might not be copy assignable, we do correctly the job. We copy the value from from the source argument, and if the type is copy assignable, we just use that copy assignment to initialize to copy assign the source value rather. So for move assign, we have to do kind of the same thing. If the type provides no throw move assignment, we use that to move the value from the source argument to this instance. And if it doesn't provide move assignment, no throw move assignment, we destroy this object and move construct the other object. And we can do that because move construction is guaranteed to be no except for small object, because we specifically have written that condition to express that. So for big objects, we have to do kind of the same thing. For assignment, we have assignment if the type supports copy assignment. And if it doesn't, we have to destroy the old value and copy construct rather the new value. And for move assign, this is very similar. If the type provides no throw move assignment, we use that to move assign the value. And if it is not, we destroy the old value and move the pointers to from the source argument to this instance. I hope it makes sense to this point. We need to do a couple of small changes. In the copy assignment operator, we have to add this piece of code, which checks if the instances contain the same type. We can do that by comparing the pointers to methods. If the types are the same, the pointers to methods will point to the same tables, function tables. And if they are the same, we can call our assign method. And we just short circuit this whole function and just return. For move assignment, this is kind of similar. We check if the other instance contains the same type, and if it does, we just call move assign and short circuit return from this operator. And now everything kind of seems in its place. Copy construction calls copy constructor, move construction calls move constructor, assignment calls assignment, and move assignment calls move assignment. We can be happy at this point. So since I see no questions, I will continue with a couple of more slides. We can add other things. In our case, in this example, it is in place and value assignment, which allow us to in place a value without explicitly passing an instance of that type. Here it is. And the other one is value assignment, which allows us to pass the instance, the value of that instance inside an existing object. So in this case, we have to constrain it so it receives only, or rather allows us to construct only types that are derived from our interface. The function itself receives a bunch of arguments and returns a reference to the actual type. So here we check if this instance has value, and if it does, we destroy this instance, assign the pointer to methods null_there, because we want to the weak exception guarantee at least. Next, we construct the instance itself. If the type is small, we just use placement new to construct the instance from the provided arguments. We perfect forward the arguments. And if the type is big, then we just new the new instance, also providing of the arguments, perfect forwarding the arguments, and also storing that pointer to that instance into our big member, pointer to the data. Then we assign a pointer to methods with the pointer to the table for our concrete type. And then we save the pointer to interface, possibly involving pointer conversion. And then we just return. For operator, assignment operator, which assigns arbitrary values, we have to, we can do this. So if the type is assignable from the, if the type, how do you say? If the type that we want to construct is assignable from the argument, then if this instance contains exactly that type, we can use just assignment that is, we checked that is supported. And for small object, we just reinterpret cast the address to small buffer to that type and just perfect forward the argument. Otherwise, for a big object, we static cast it to pointer, reference it, and again, perfect forward the arguments and assign it. And then we are done, we can return. And this kind of shortcut will work in case the type supports assignment from the argument. It can be either R value reference or L value reference or whatever. And this instance of this wrapper contains the same exact type that we want to, then we would like to construct. Otherwise, it's kind of similar to what we already saw. If this instance has value, we destroy the value, assign the pointer to methods not there, because we want weak exception guarantee, and we call construct function, which is identical to the contents of the constructor that we saw toward the beginning, and we assign the methods pointer. So yeah, here it is. And then we return. The construct function contains identical code that we saw in the constructor, so we can refactor a bit and just replace the code in the constructor with code to this function. And we have 6 minutes left, and we kind of on time. And let's discuss what else could we have. First of all, we have to enforce that all the types we want to put into our value wrapper are copy constructible. This is modeled after std_any, which requires that all the types that we want to put into std_any are copy constructible. So we can do this by just slapping that requires clause across all the functions that receive some template types, template arguments. So what else can we do? We can implement in place constructions, again, modeling the interface of std_any. We can add reset capability, reset call or function or method, but we kind of have this already if we just assign an empty instance. We can use swap. We can add swap probably. That should maybe behave more efficient than if we use default algorithm for swap, for example, from standard library. And kind of the most interesting question is, should we use function tables or pointer to function tables, or should we use do all so-called functions like libstd C++ and libc++? What are the performance trade-offs and what are the binary size trade-offs in this case? I haven't had time to investigate it, so it's an open question for now. And this is kind of it. Thanks for listening. We have 4 minutes for questions, for possible questions. So, okay, I guess I will be in the Q&A room in Gather Town in like 5 minutes, and we can discuss any question there. Thank you.